Design of DC plasma torches. The plasma torch is designed to obtain maximum thermal output. The increase in efficiency not only helps in achieving better heating of the gas but also in reducing electrode losses and thereby increasing the life of the electrode. The design also ensures that the erosion rates of the electrode are kept to a minimum. The parameters which affect the performance of the torch are cathode size, its taper near the gap convergence of the nozzle, nozzle orifice diameter and orifice length, electrode gap and cooling of the electrode, the cathode. The taper at the tip and diameter of the cathode affects the drop across the cathode rod. Tapered rods with slightly blunt tips are used for non-transport applications, while for cutting applications, a flat disc should sloped on the edges is used. The taper angle for nitrogen is kept larger than that for argon, about 45 degree. The taper angle or sloping of the disc is usually smaller or equal to the convergence angle of the anode nozzle. For spraying and cutting, 10 mm dia cathodes are used, while for welding electrodes of 6 mm dia are used. The cathode is pressed to fit into a water cooled copper holder and braced to it. The general guidelines for designing the torch are: large currents require a larger orifice diameter cathode, orifice length, and electrode gap. While operating at larger arc voltages, it is preferable to increase the angle of taper at the cathode tip by the same token same taken while operating in the transferred arc anode. High arc voltage flat face cathodes are used. For avoiding turbulence, the edges of the construction are rounded off and smaller cathode diameters are used. To stabilize laminar flow modes, a large orifice length to diameter ratio is used. In any torch, the alignment between the electrodes is very essential, and any misalignment would lead to undesirable arcing on the sides and non-uniform erosion on one side of the electrodes. Non-transferred arc modes are long throat length, while for transferred arc mode, the minimum orifice length is used. The cooling provided to the cathode should be optimized for minimum uniform erosion without cracking the cathode and destroying the maximum stability. The cathode taper and convergence of the nozzle should be such that the arc terminates at the tip of the cathode. This usually means that the tip is nearest point to the anode. Oxygen or compounds of oxygen in the plasma gas are detrimental to the cathode, and by the same token, no water leakage into the plasma chamber from the chamber cooling of the electrodes should be allowed. Physical configuration. The variables such as standoff distance, angle, depth of cut, feed, and speed of the work towards a torch are playing an important role in plasma cutting. The feed and depth of cut determines the volume of metal removal. Figure shows the metal removal as a function of the torch angle. Stainless steel, mild steel, as well as aluminium in thickness up to 25 mm can be cut at speeds up to 2.5 meter per minute, with best quality occurring at about 1 meter per minute. Work environment. The environmental variables for plasma cutting includes any cooling that is done on the cathode, any protective type of atmosphere used to reduce oxidation of the exposed high temperature machined surface, and any means that might be utilized to spread out or deflect the arc and plasma impingement area. But in this field, very little work has been done to investigate the effect of these techniques on operation.